Thank you for joining us for the Varnish Overview webinar by Fluid Life. In this webinar, we will be reviewing 4 key areas. What is varnish? How is it created? What impact does it have? And what you can do about it. So let's get started. First, we will discuss what is varnish. Varnish is a major issue that is found where oil flows and can lead to unplanned downtime and major outages of equipment. Varnish is a hard, thin, sticky substance that will deposit or plate itself onto internal surfaces of equipment. These internal surfaces are ones that come in contact with the lubrication oil of the equipment. These surfaces can include gears, solenoids, oil channels, pipes, sump tanks, and bearings. Anything that requires lubrication or to some extent come in contact with the oil can be susceptible to varnish buildup. Varnish is an oil-insoluble product that is seen as a contaminant to a system. Varnish is sometimes identified as a sheen, a sludge buildup, a lacquer, shiny-like reflection on surfaces, a yellow tinge, or having a burnt appearance. Varnish is also interesting as it can exist both as a soluble and insoluble form in oil. And depending on the saturation and heat of the oil, it can bounce between the two. A usual encounter with varnish is right at your home in the kitchen, your frying pan. Let's assume you are using your favorite pan to create your favorite dish. You set the pan down on the burner, warming it up. You add cooking oil, swirling it around to provide a non-stick coat. You add the ingredients, stirring occasionally to prevent hot spots and burning. Something distracts you for a moment, and when you get back to the pan, you can tell the oil is sizzling and burning. You stir more, finish your dish, and come back to the pan later for cleaning. You notice the yellow sticky glaze on the pan that's super hard to get rid of. That's varnish. The frying pan serves as a relatable example of varnish, how it is visible, how it is created, and ironically, how the oil that was meant to prevent sticking is now causing the opposite to happen. Varnish is a hard, lacquer-like oil-insoluble substance that is difficult to remove from components. As mentioned in the frying pan example, it usually looks like a burnt or yellow sticky coating as shown in the image on the top left. When large quantities of varnish accumulate in the oil, they begin to precipitate out of solution into a thick, gooey layer of sludge. Sludge is usually a varnish precursor and is a soft, pliable residue, as shown in the picture on the top right. The term varnish often refers to both sludge and varnish, and are the result of lubricant degradation. As varnish and sludge collects, it will eventually block the flow of lubricant and cause major issues. In this next section, we will review how varnish is created. Oxidation of oil occurs in the presence of air, oxygen, and heat. Varnish is the result of oil degradation initiated and caused by oxidation. Oxidation is always occurring in oil to some degree and is handled by oil additives known as antioxidants to counter or combat its impact. However, when oxidation levels go beyond a level of control or management, these additives will become challenged and varnish will form. Oxidation reaches this problem level when it is induced by excessive heat or by heat and an accelerator. Once oil becomes oxidized, it will not lubricate well and cause additional issues in your systems. Varnish is a symptom of an underlying cause, that cause being oxidation of the oil. To understand how varnish is created, you need to understand how oxidation comes to be in your oil. Oxidation is a chemical change that is occurring in the oil when it reacts with oxygen. This change occurs at a molecule level. It is a complex series of reactions that can be categorized into 3 stages: initiation, propagation, and termination. The reaction results in the sequential addition of oxygen to the base oil molecules to form a number of different chemical species, including aldehydes, ketones, hydroperoxides, and carboxylic acids. A general fact about oxidation rates is that it will double for every 10 degrees Celsius rise in temperature above 75 degrees Celsius. During the initiation stage, hydrocarbon molecules react with various catalysts, leading to the formation of free radicals. Free radicals are among the unwanted results of the intermediate reactions within oxidation. These highly reactive molecular fragments contain one or more unpaired electrons that are prone to reactions with hydrocarbons and other molecules. They can steal one of the electrons of other molecules and start a reaction of oxidation. Propagation refers to the complexity of additional reactions of various types of free radicals and catalysts that result in the production of more free radicals and oxygenated compounds. These catalysts can be wear metals, which can cause or accelerate oxidation, UV light, direct sunlight, or uncommonly high temperatures. Termination is the endpoint of the oxidation process, which can be a positive or negative result. Positive would be that antioxidant additives in the oil succeeded in negating the effects of oxidation. For this presentation, the focus is on the negative result, or the formation of varnish. There are multiple scenarios that can cause high levels of oxidation. You can sum up the origination of oxidation in 3 categories: thermal, chemical, mechanical. Each of these causes have a number of underlying reasons that are attributed to them. Each cause can act individually towards oxidation or be a combination. For example, in this kitchen fire, consider what caused the fire. Was it a pan fire? This is a thermal factor. Did your creme brulee recipe go wrong? This could be a chemical factor. Was it an overloaded circuit? This would be a mechanical problem. All of these scenarios or factors can lead to the same outcome, in this case, the kitchen fire. Our first factor is thermal. Let's go back to our frying pan analogy. The oil in the pan is an example of being subject to an external high heat for too long. With the ingredients being stirred, the oil would have had the chance to not be exposed to the burner heat for too long. It was being circulated. This would be similar to dead legs in a system. The causes found here are heat stressors in the working environment or a condition in the equipment that is creating excessive heat. Thermal issues do not necessarily require an oxygen source, they simply require a heat source. Your working environment can create thermal stressors on your lubrication system. One way is if the ambient temperature of the room is high. Even if the oil is being circulated to cool it, room temperature could prevent it from reaching a point of sufficiency. It could also be due to a lack of air circulation in the working area or where the cooling vectors are located. This can accelerate depletion of the oil as antioxidant additives are being used at a faster rate than expected. Examples of this could be in a die casting mill or high humidity areas in a paper mill. Another way the working environment can impact on oxidation is some part of the system is subject to a hotspot occurring from an external source. This source could be an exhaust from a neighboring piece of equipment heating up a piece of pipe that is circulating oil. Large turbine or hydraulic systems that have a large footprint in the plant can have these situations. Equipment unintentionally being insulated could be another issue. This insulation can be from original design of a section being too close to a wall, or materials being stored closely, or some sort of new floor work around the original equipment such as a walkway built over a section. As well, dusty environments coating the equipment in a thick layer of buildup can cause insulation. Finally, KPI and productivity quota demands may exceed recommended limits by the manufacturer. While the equipment is technically capable, there may not have been consideration given to the lubrication of the system and if it can sustain the limits set. Equipment design can also impact on oxidation and create thermal stressors on your oil. Equipment that is made to be more compact and have a smaller footprint on the floor may require lower volume sumps or reservoirs. This puts more thermal stress on the oil that exists as it lacks the cooling effectiveness of having more volume. Another equipment design issue could be that the oil cooler is insufficient in cooling the oil. The cause of this failure can vary from issues with the cooler lines, cooler pump, cooling oil loss of heat transfer capabilities, or faulty sensors. Common around pumps, hydraulic packs, and bearings is the occurrence of microdieseling. Microdieseling is when micro-sized air bubbles found in the oil are trapped and compressed, causing an explosion. This quick change from low pressure to high pressure causes the bubbles to pop. These explosions are also micron-sized but have a big impact on the oil and surface surrounding it. The result is carbonaceous deposits forming on the nearby surface and appear as a dark brown varnish. This is similar but not the same as cavitation failures. Most oils are fairly non-conductive. However, as oil flows through lubrication systems via pumps, pipes, valves, and filters, static electricity builds up. Because oil has low conductivity, the oil retains the static charge instead of discharging to machine surfaces. As the voltage increases, dielectric breakdown can occur, causing arcing from the oil to a metal component within the system, much like a lightning strike. The resulting sparks can reach temperatures of 10,000 degrees Celsius or more in an instant, which thermally stresses the oil and causes deposits to form. Depending on the situation, special filter media can be deployed within the oil filtration system to help dissipate static charge and prevent voltage buildup within the oil. Oxidation can also occur when the oil is undergoing a chemical change that is directly impacting its ability to control oxidation. The chemical change to the oil can occur through the introduction of contaminants, shearing, or the natural result of oxidation itself. These changes can be caused by internal and external contamination factors or exacerbated by the oxidation itself. Oxidation begets oxidation. Internal contaminants are found within the unit itself. Copper and iron are common metals used in pumps, engines, servos, and other components and are often found in varnish-sensitive equipment. As the unit operates, there is a certain level of wear and tear occurring. Copper and iron-wear metals act as catalyzers for oxidation and acidity to occur in the oil, leading to varnish production. Water contamination will react with the oil in a process known as hydrolysis. Hydrolysis, in the presence of heat and wear metal particles, will promote the acidity of the oil. There are 4 types of acids, including aldehydes, ketones, hydroperoxides, and carboxylic acids. Acidity from hydrolysis is carboxylic in nature. Carboxylic and oxygenated particles react to each other and form sludge and varnish, among other problems involving corrosion and viscosity. Therefore, monitoring acidity levels is important. To avoid water contamination, educate maintenance staff to avoid direct shedding of water at ingression points such as shaft seals, dipsticks, fill caps, and breathers. If water spray is inevitable, use passive shields and deflectors to avoid direct water spray in these areas. Another way to reduce water incursion is to use high-performance seals that experience less wear and offer better protection against contaminants. You should also regularly inspect and maintain gaskets on fill caps and hatches and replace dipsticks with level indicators. Additionally, you could replace basic vent breathers with desiccant breathers, which dehydrate incoming air, or an expansion chamber, which allows the system to breathe without ingesting external air. Today's lubricants are formulated with a careful balance of additives and base stocks to match the lubrication requirements of the equipment in which they are used. Mixing lubricants can upset this balance, leading to mechanical problems and shorter equipment lifespan. Some lubricants are incompatible because of additive chemistry differences, which can lead to undesirable chemical reactions, including the formation of insoluble material which deposits onto machine surfaces. Another common reaction stemming from lubricant incompatibility is when an acidic component in one oil reacts with a basic component in another, and often accelerated by water and heat. This can also form harmful solids in the oil, leading to severe oil degradation and formation of sludge and varnish. In this next section, we will review the impact of varnish on your equipment and oil. Varnish is detrimental to any piece of equipment and impacts different components in different ways. The inevitable outcome is lower efficiency from your equipment, accelerated degradation of components, reduced efficiency of filters, or the plugging of filters' inlets and strainers, which will eventually cause catastrophic failures. Varnish is a sticky issue. Any component that requires smooth operation, such as bearings, shafts, or valves, will be negatively impacted. Varnish reduces the clearances needed for the lubrication regime. The lubrication required to allow for efficient movement will instead be met by added friction from the sticky varnish. The efficiency of movement is impacted at this point as there is added effort or energy needed to overcome the varnish and move the component. At the equipment level, this can generate more heat on the surface or downstream from the component. For example, varnish deposits on the shaft could require a gearbox to run harder and likely hotter because of the increased effort to turn the shaft. Efficiency loss can also be measured in cooling capabilities. Cooler lines built into a sump can be prone to varnish buildup. As the oil heats and cools, any soluble varnish can plate off more easily on the cooler lines. This layer of varnish will begin to act as a thermal shield, reducing the capabilities of the cooler lines to keep control of the oil temperature. Without accurately being able to control temperature, the oil can heat up past operational limits. Additionally, varnish can plate off on sensors, which impacts their ability to properly monitor the true temperature of the oil. In this case, the oil may be detected as too low of a temperature, and in response the cooler lines will adjust to allow the oil to heat up more, while in reality the oil is unintentionally now being heated up beyond operational limits. Efficiency loss from varnish can also impact on production. With slower movement of the component presence, there are fewer cycles that a unit can perform in the same time frame, such as in an injection molding machine. Turbines are another example of where production can be impacted. Varnish tends to target servo valves, causing them to stick and either delay movement or not move at all. This can cause startup failures or trigger the turbine to be taken out of operation. For turbines needed to support peak kilowatt demand, a failure to start or a shutdown in operation because of stuck servo valves can cost hundreds of thousands into the millions of dollars from both a lost production and repair perspective. Varnish can also cause direct and indirect component wear. Because varnish is a sticky substance, a direct impact of varnish occurs when particles embed themselves into the varnish and act like sandpaper. Not only does this impede flow with added friction, but can cause severe issues with anything that has tight tolerances or surface-to-surface contact. Servos, valves, actuators, pumps, and gear teeth, for example, would encounter additional wear from this sandpaper-like reaction. An indirect impact of varnish is through the products of oxidation. Oxidation is a product of various sources such as acidity, heat, microdieseling, and water, and will in itself cause wear. Acidity can lead to corrosion of internal components. Microdieseling causes soot particles that are abrasive. Water causes an array of problems, including changes to viscosity. Given enough time and circumstances, varnish can occur in nearly every piece of equipment, but there are some where varnish proves to be a larger problem. This can be due to the susceptibility of varnish forming due to the oil types in use, equipment conditions, or problems posed from an operation standpoint due to the criticality of the equipment. Oil types do matter with respect to the formation of varnish. Let's start with types of oils, which refers to the base oil that is being used by the lubricant. Base oils act as the foundation of the oil before additives are introduced into the blend. Imagine a cake. Cake comes in all shapes, sizes, colors, and flavors, but all have the same core ingredient to make them, which is generally some type of flour. Base oil is like the flour, and everything else is just additives. There are 5x different kinds of base oil groups as categorized by the American Petroleum Institute. Each base oil group is defined by what the oil is made of and how refined it is in the manufacturing process. This determines if the oil can be classified as mineral or synthetic base, and other characteristics that may impact on varnish control. Groups 1, 2, and 3 are refined from petroleum crude oil and would be classified as mineral oil, although Group 3 can be described as synthetic oil. Essentially, the longer it is refined, the purer the oil is, as it has less saturates and contaminants, and higher grade it is. Group 4 are classified as PAO or polyalpha olefin oils. These are the most common synthetic base oils used in industrial applications. This base oil is refined completely from a synthetic hydrocarbon that is comparable to that found in mineral oil. Group 5 is all the other base oils. If it is not a mineral oil or a PAO, it then falls under Group 5. These other base oils include phosphate ester, or POE, polyglycol, polyester, diester, perfluoropolyether, and silicone oils. These oils can be mixed with PAO or synthetic oil for its benefits, but still would be classified as Group 5. Solubility is the property that allows a lubricant to hold polar substances like varnish in suspension without damage to the machine. Oil solubility increases at higher temperatures. Group 3 oils have lower solubility than Group 2 and Group 1 oils. There have been many instances of machines experiencing varnish deposits due to lower solubility of the oil after switching from a Group 1 oil to a Group 2 or 3 oil. Out of the 5 groups, there are numerous base stock oils that can be used, and there are 6 that are in dominant use as base stock for lubrication oil. We will review the 3 major types that account for 80% of lubrication oils used: PAOs, phosphate esters, and polyglycol. All perform differently to each other when tackling varnish. PAO-based lubricants are often used in automotive, hydraulic, geared, and bearing oil systems. They have high thermal and oxidative stability, are wax-free, and tend to leave less varnish and sludge. However, their low polarity can lead to poor solvency, which means they are not efficient at cleaning or removing varnish and sludge. It's common for PAO oils to be blended with ester stock in order to allow additive solubility, as the oil alone has limited additive solubility. Phosphate ester oils work well in high heat environments as they are fire resistant and provide great wear resistance. These oils, however, are not suitable in environments where water is present, as they react quickly and very easily with water to produce alkyl phenols and acid phosphates. This means these oils are an easy target for varnish, as this will oxidize the oil and form varnish. Testing parameters to detect varnish in these oils are limited, as acid number does not increase from the oxidation process, and high phenols on ruler test results can be a bad thing. These oils are twice the cost of PAO oils and 4 times the cost of mineral oil. Water-soluble PAG oils are incompatible with petroleum oil, and care must be taken in transitioning equipment from hydrocarbon oils to PAG oils. Although PAG oils have long been used as industrial lubricants, recent work has led to the development of PAG lubricants for use in equipment in the food processing industry. These products are known as food-grade approved lubricants and are also a common OEM factory fill for compressors. PAG oils are often used in high-temperature applications such as compressors, turbines, heat exchange systems, and have excellent deposit control, as degradation products are soluble in PAGs. These oils are resistant to varnish formation and have great heat transfer performance, along with thermal and oxidative stability. PAGs are available in both water-soluble and insoluble oils, but they are not compatible with mineral oil-based lubricants. System change-outs can be more time-consuming and costlier because of this. One thing to watch out with PAGs is seal compatibility, as they tend to shrink seals. The formation of varnish or its impact weighs differently depending on the equipment, and in some cases, varnish can pose serious problems. The reason could be that the nature of the equipment makes the formation of varnish particularly easier, or that the effects of varnish are much more impactful. In these systems such as turbines, air compressors, hydraulic systems, geared components, and engine fuel lines, the monitoring, control, and mitigation of varnish is more essential. The result of unchecked varnish in these systems is more severe from the perspective of wear, downtime, or criticality of the unit. Power-generating turbines are high-value pieces of equipment. Turbine reservoirs can be in the 1,000s of liters capacity and must be monitored for varnish control, as the bulk of the oil stays in use for a long period of time. This reservoir can be used for a number of other components, in addition to the turbine, such as pumps, servos, and bearings, that together serve as one system. Turbine systems are complex and encounter more situations that can make them prone to varnish buildup, such as micro-dieseling after a pump, dead legs in oil channels, or electrostatic discharge near filters or reservoirs. Because criticality of the turbine unit is significant, keeping downtime to a minimum is a priority. Because the cost of replacing that amount of oil is high, and because of long-term use of the oil, testing for oxidation, acidity, and varnish levels in the oil is critical. The oil type for turbines is generally heavily additized with antioxidant, and it is also a low-conductivity oil, highly dielectric, which increases the chance of electrostatic discharge. RPVOT, ruler, acid, oxidation, varnish MPC, and wear metal testing should be done regularly to monitor additive levels and ensure the system isn't in jeopardy of varnish or other fail situations. There are 3 common types of compressors: rotary screw, vane, and reciprocating air compressors. Each perform the same task in a different manner, which is to compress air and channel it for use. Most common type of compressor we see are screw and rotary compressors. The use cases for compressors range from refrigerators to HVAC systems and pneumatic tools. Therefore, compressors are found in a variety of industrial settings, from small shops to mills and factories. PAG oils are common for compressors and are prone to oxidation due to thermal and chemical factors. Compressors are high-heat components that make them a target for varnish issues. These systems are also dependent on clean air. External contaminants such as poor air quality, such as acidic caustic air in the environment or humidity, can affect the oil as it's being compressed into it. Hydraulic systems are composed of multiple sections with pumps, servos, and long sections of piping. Hydraulic oil channels have tight tolerances and need to be kept clean to handle high PSI applications. The most common oil type for hydraulics is PAO. Hydraulic oil can be in a large high-volume setting with a single reservoir for multiple systems or smaller scale, such as a 25-liter sump on an excavator. Varnish in hydraulic systems can be very disruptive and lead to full failure of the system. Some effects of varnish include sticking to servo valves, pump blades shearing and breaking, a loss of performance such as slow movement of excavator arms, or an incomplete motion sequence on a screener. Geared components will have tight tolerances between the gears. Gearboxes can be subject to high heat situations due to environmental conditions like heat and humidity in a pulp mill, or high internal operating temperatures. These situations can cause varnish to plate out and cause the shearing of gear teeth due to varnish stickiness. Engines are generally operated under high heat for extended periods of time. As a result, engine oils can experience additive depletion and become heavily oxidized, forming sludge and varnish on components. Additionally, external ingression of water or coolant leaks can lead to acid formation, corrosion, and varnish. Finally, fuel lines and injectors will varnish when fuel is stagnant in the lines or tank separation occurs as the fuel deteriorates. This separation is a chemical change of the fuel as it polymerizes, oxidizes over time. Moisture condensation combines with the ethanol in the fuel will lead to varnish production. In this final section, we will discuss what you can do about varnish. Given enough time, oxidation will occur and varnish is inevitable in any oil. The goal is to have control of the production of varnish and to keep it within a tolerable limit. Knowing the limit of your system, its current varnish state, and when to act are part of the monitoring and mediation efforts of varnish. You can monitor varnish by doing regular oil testing that includes the following test slate: varnish, MPC, oxidation, RPViot, acid test, ruler, and contaminant, and wear metal testing. Let's review each of these tests. The varnish potential test is also known as MPC, ASTMD 7843. This test is used to determine the likelihood that varnish could occur, is occurring, or is present in an oil. The higher the MPC value, the greater the risk. Fluid Life has a condemning limit of 25, while oil remediation services may have it lower at 15. The test begins with a sample of oil being heated to 60 degrees Celsius for 24 hours. This is a temperature that exceeds normal operations on most equipment. The sample is then left to cool for up to 72 hours and then poured onto a patch which changes color, dependent on the severity of the varnish. The darker the color, the higher the MPC value. The color of the patch is screened by an instrument which provides the MPC result. What is important to note that the MPC test does not measure varnish directly, but only the potential for varnish to occur. If antioxidant properties are low or depleted in an oil, then it would be expected to perform poorly in this test. Oxidation is a chemical change that occurs at a molecular level in the oil when it reacts with oxygen. By testing oxidation levels, you can determine the stability of the oil. Fluid Life uses an FTIR instrument to determine oxidation value of the oil. The instrument shines infrared light on the oil and measures the absorption rate of the infrared light from the oil. Simply put, more absorption of light equates to high oxidation. On Fluid Life reports, you will see the oxidation result as a number indicating the absorption rate per 0.1 millimeters. When the light is shown and absorption occurs, it measures it using a curve which is in millimeters. This curve generates peaks as you would see with ruler testing. The higher the peak or greater the space between the baseline peak and use oil peak, the greater the oxidation of the oil. Generally, an oil begins to get flagged for oxidation at 20 absorption rate per 0.1 millimeters. However, it is important to know what the baseline absorption rate per 0.1 millimeters is. If the baseline is 15, then a value of 20 is not too significant. For the most part, new oils are under 10. Turbine oils tends to be lower at 5 or under. The rotating pressure vessel oxidation test is a torture test subjecting the oil to an environment of extreme stress. These stressors are water, a copper rod, and a high-pressure source of oxygen being introduced to the oil. The antioxidants present in the oil put up a fight until they are all consumed. The result of the test is to determine the antioxidant capabilities remaining in the oil. If the oil drops to 25% of reference, it is considered unacceptable and should be dealt with accordingly, such as to drain and fill or do a top-up. The test begins with 120 milliliters of oil, 5 milliliters of water, and a copper rod. The oil, water, and rod are sealed in a container and pressurized to 90 psi. A bath is heated to 150 degrees Celsius, and the sample is placed into it. The sample is rotated at 60 revolutions per minute. As oil oxidizes, the pressure builds up. The time is then calculated for how long it takes for pressure to build to 175 psi. The higher the number, the better. Monitoring acidity levels acts as a precursor to varnish formation. As discussed earlier, acidity is a chemical change of the oil that occurs from water as a consequence of contaminant or condensation or oxidation itself. Fluid Life has two separate methods to report acidity levels, by the FTIR instrument or by TAN, formerly known as total acid number, ASTM D664. Each method obtains the result in a different fashion, but both will report the findings as the same unit of measure. This unit of measure is the quantity of base, usually potassium hydroxide, KOH, expressed as milligrams of KOH required to neutralize the acidic constituents in 1 gram of a sample. The total acid number test determines the acidity of an oil by measuring how much potassium hydroxide is required to bring the oil to neutral. The more potassium hydroxide required, the greater the acidity level in the oil. A result of 2.5 milligrams potassium hydroxide per gram would indicate that the oil was rather acidic. With the acid number by FTIR method, acidity level in the oil is evaluated using infrared light absorption. The higher the absorption, the more acidic the oil is. The value obtained by absorption is presented in the traditional milligrams potassium hydroxide per gram unit of measure. This is for it to be consistent with the industry standard value provided by TAN method, since FTIR method is an economical in-house method. Initial pH is a measure of the pH level of the oil and provides a measure of the strength of the acid present in the oil. The result is the value used on the pH scale, where 0 is acid to 14 being alkaline. Acid number generally represents how much acid is in the oil, while initial pH confirms the strength of the acid. These measures are often used together. RULER stands for Remaining Useful Life Evaluation Routine. RULER determines the health of the oil by testing the phenolic and aromatic amines in the oil. Phenol and amines are antioxidant additives formulated into the oil. The levels of these additives are used to monitor and help determine the life left of the oil. The result is presented in a simple percentage form, with 25% out of 100% typically being the condemning point of the oil. Performing RULER testing on a steady basis provides an easy-to-understand visual trend of the oil. You can see the gradual percentage change in the health of the oil, and use these results to determine oil change intervals, extended oil change intervals, or timely replenishments of the antioxidant additive packages. RULER test operates by running a specific voltage, voltammetry, through the oil that reacts with the phenols or amine additives. The resistance or absorption of the voltage generates peaks on a graph. Depending on the level of these peaks and in comparison to a reference oil, you can determine the amount of phenol amines remaining. Contaminants found within AA system are likely culprits of accelerated oxidation. Water is a common contaminant that can create acidity and eventually varnish. Carl Fisher water percentage and crackle tests are two tests that can validate if there is a presence of water in the system. Crackle is a simple test where the sample is placed on a hot plate. If there is presence of water, then the oil will crackle. Carl Fisher is more technical and quantifiable, as it will present its findings as parts per million or a percentage. Certain wear metals like iron and copper can act as catalysts for acid and oxidation rate with the presence of water. These metals are commonly found in pumps, governors, bearings, and hydraulic systems, which are all used in turbine systems. ICP spectrometry is the standard way to monitor wear metals and detection of these elements. If varnish testing indicates varnish is present, there are various options available for mediation and removal. To start, determine the root cause of the varnish in the system and reclaim any oil in the system currently in use. Then assess how and when the issue can be resolved. If that time frame is not viable because it creates too much downtime or is too far in the future, then the emphasis should be on mediation efforts. One mediation approach is to flush it out over time with new oil top-ups. This is a relatively simple procedure, but only works to a point. Oil needs to be warm and in service for the varnish to be soluble in the oil and not plated out. As new oil and additives are introduced, this will slowly scrub away existing varnish. However, this is not an ideal approach if the presence of varnish is more severe. This can be a costly and slow process, which can take years on a large volume reservoir. Another option is to chemically flush out varnish by using a cleaning agent that is circulated in the oil. The cleaning additive is a solvent which is added to the existing oil in a 5 to 20% concentration. Generally, this is an oil-compatible and inexpensive procedure upfront and usually takes between 1 to 30 days. Once the cleaning cycle completed, a drain and fill is recommended. However, performance impacts and complications can occur while the cleaner is being used, such as premature oil filter plugging from solid contaminants built over years now being released and filtered out. Oil filtration systems have different approaches to tackling varnish. These systems can remove varnish from the lubrication oil without the need of top-ups or cleaning agents. Filtration systems are looped into a system and run live with the equipment. Electrostatic separation and adsorption media are two popular methods of removing varnish. These technologies can only remove soluble or insoluble varnish particles. They cannot remove varnish deposits that have formed inside the unit. The oil would be the scrubber on these deposits, which the filter would later catch. Electrostatic separation works by using an electrostatic charge to attract varnish particles to a filter media. An offline or kidney loop system is connected to the reservoir with the oil running through the media, then back into the reservoir. In this system is an electrostatic field that provides a negative and positive pole in the field. Varnish particles are typically polar, and when passed through this field, the particle will be attracted to its opposite pole, either negative or positive. These devices do work quite well and are gaining popularity in their success and ability to remove soft particle contaminants. However, they work well within certain conditions. There must be no water presence in the oil, as water compromises the electrostatic field. Another condition is that the oil does not contain detergent or dispersant additives that would hold contaminants in suspension. Additionally, these filtration systems cannot be used in high-pressure situations. Because the flow rate of these systems is quite low, it cannot filter a large volume of oil quickly. These are not one-pass systems and would need to be run continuously for an extended period of time to achieve results. Adsorption systems can also be connected to the system as an offline or kidney loop system. These can be installed in high-flow situations and can filter large amounts of oil quickly. These dense activated carbon or silica gel media filters remove varnish particles and other contaminants such as water and wear metals, like copper and iron. In this case study, Power Generation Station ABC noticed efficiency issues in a peak power turbine. The hydrostatic lift servos were not in sequence, and they noted the oil in service was at the halfway mark of life, or 7 years old. Their peak power turbines were used intermittently when needed and underwent more stop-start-stop operations. Oil samples taken from the heated reservoir showed expected levels of degradation at this point of oil life. Additional samples were provided from an alternative spot near the pump for the servos, which indicated that varnish issues were evident. Based on their investigation, it was found that once the oil left the reservoir and traveled along the pipes, it cooled down slightly once it reached the pump. When the oil arrived at the servos, the varnish was plating off little by little. Because of the nature of the large, complex lubrication system, it allowed varnish to form and deposit without being seen at the reservoir to any alarming degree. To solve this issue, an inline filter was installed pre-pump. Varnish was removed at this stage, and they allowed the oil's scrubbing abilities to passively clear up the servos. Now, let's review some of the key elements about varnish we discussed in this webinar. Varnish is largely the result of oxidation. Oxidation is always occurring in oil. Varnish impacts the operational efficiency of equipment and eventually can cause failures. Varnish can occur in all kinds of equipment. Some are at greater risk of varnish formation or in greater danger of its effects. Varnish can be detected, monitored, and mediated. Varnish can be reversed to a degree. Thank you for your interest, and we appreciate your time to watch this webinar. If you'd like to learn more about how to monitor and manage varnish in your equipment, contact the Fluid Life team at 877-962-2400. Have a fantastic day.